is the lecture from the Bourgogne, and his first lecture is titled Recurrent Class of General Diffeomorphisms.
When I asked about what is the audience, the answer was we don't know. So other students, at least one, two, three, yeah.
PhD students included.
PhD students included, yeah. Okay, because I prepare for students. If there was no student, next course would be faster. But if there are students, I will go. I will continue as I prepared. Okay, the first time I meet some result of decomposing or decomposing the dynamic in pieces was, I think, as many people in a small paper, differentiable dynamical system in 67, where he first defined a class of dynamical system he called axiom A plus no cycle condition. So it's some kind of very technical name, but I will not define today. But so this class is important because first, when you are axiom A plus no cycle conditions, then the place where the dynamic is interesting, that is the place where there are recurrence, is structurally stable, meaning that you perturb your dynamics on the place where you have recurrences remain conjugated to itself. Okay, so indeed, it will characterize this what is called omega stability. So this name means precisely that the place where you have recurrences don't change when you perturb the dynamic in the C1 topology or CR topology are larger than 1. These dynamical systems have so there are diffeomorphisms on smooth manifold, or it can be also vector field on smooth manifold. But one of their characteristics is that the global dynamic split in pieces. So let's make a very rough picture. You assume your manifold is here, and what you get is that you can break your manifold in pieces where the dynamic is only going down. So you have several levels, and if you take any two levels, between them you have your piece, that is, most of the orbit will go from the top to the bottom, but some enter and don't go to the exit. Some other, at the contrary, go out and do. But there are also few orbits which remain, which pass also life in this piece. So this kind of decomposing your manifold will be called filtration. That is, you will have the big one, which will be, so the empty set will be M0, and it's included in M1, included in M2, and so on. And you have an MK. And if you look at the orbit which remains in between two levels of the filtration, that is, you look at mk minus 1 minus mk, and now you want to know who remains all the time there. For that, you make the intersection of the iterative. So it will be H here, another morphism. You make the iterate of the Hn in Z. On that, the orbit, some point in this intersection is the point so that each iterates remain in the level, and that will be so a compact invariant set. And this compact invariant set will be transitive. So let's call that lambda k. Lambda k is compact. Invariant means that h of lambda k is equal to lambda k. It will be transitive. So transitive, I don't know, so I guess you already have seen topological dynamics, but I think the meaning of transitive change in the between the past and now. So the transitive was there exists a dense orbit. But now, so I will not use this. I will use there exists a positive, a dense positive orbit. Positive orbit means that you so there exists x in lambda k, so that if you just consider the f e of x I positive, then that is equal to lambda k. So why is this difference? This difference is to avoid this case which is that I don't want. You take an orbit x, which has its iterate, which go from one point to another point. So this compact set here could be called transitive because the orbit of x is dense, its closure, but is not so interesting. This notion has a name also, which was topologically ergodic. Topologically ergodic. But I think more or less in 2000, people started to forget this kind of, they start not calling more this kind of dynamic to be transitive, and so topologically, for me, transitive is equal to topologically ergodic. So I prepared for students. I also prepared exercise. It's not for being obliged to make exercise. It's more for thinking of part of the classic course that I will not make for not being too slow. So take. I don't know, K, a compact metric space. And show that it is transitive in this sense, so transitive, or as you prefer, topologically ergodic. Is equivalent that for any two open sets non-empty, becomes a chipset, there exists n strictly positive so that Fn of U intersect V, and that is also equivalent that generic. So there exists a J delta dense, so generic points have positive or negative dense orbit. So the omega limit point x, the omega limit of x is k, and it's equal to the alpha limit of x. Okay. So that's a nice property when you have positive dynamics, so generic points at dense orbit. As another exercise,
I think most classical is about every human.
sorry?
Classical for me is this definition, that for every P and Q, there is.
Yes, so that is the classical definition. This definition implies mostly that, and you have to check that this definition is applied by the existence of a positive orbit, which is also easy. That's not difficult. But for thinking what means transitive, I think it's nice to do by yourself and not to just looking at the blackboard.
Excuse me, I guess we need some hypothesis because we people keep a space with just 2 points, and the map takes one of them to the other, and like A and B.
Sorry?
If the map, the space is a metric space with 2 points, A and B, and the map takes A to A and B to A. So it's transitive and.
Oh, sorry. H homeomorphism. So I will never consider non-injective dynamics. For that, sorry, but
Do you mean relative concepts?
I said it. So you are not listening correctly. If you want that I write it, I can write it, but yes. So there is also another thing here. This in the Smale decomposition theorem, so it's called spectral decomposition theorem by Smale. So these are not only transitive, but also they are not contained in larger transitive subsets. Why that? Because all around, all the other points in this level are wandering points. They just pass and never go back. And so there are maximal transitive subsets. Also, you can also take that if you have any homomorphism, compact metric, compact metric, then if you have any positive set, I don't know, any x, including k positive, so there exists y containing x, which is maximal transitive subset. I'm telling that because we will just see now another decomposition of the dynamic in pieces, and it will not using this notion. So this notion looks fine. If you want to look at where the dynamic is interesting, positive is a very nice property, and to know that there are maximal one could be some candidate for being the good pieces. So, but there is some trouble. So that is the next exercise. The next exercise, which is more difficult if you don't know too much things about dynamical system, is exercise is to find K having let's say, X, Y, maximal positive subset. So, H, homeomorphism from K to K. On X, Y, maximal positive subset. So that they have an empty intersection. So, okay, there are maximal positive subset, but they are not canonical. If I have some positive subset, I take some maximal, but there can be plenty of them. So it's not a good decomposition. You are not splitting the dynamic in pieces if you consider the maximal positive subset. You are considering interesting places, but not a splitting. They can meet. So, as I said, these exercises are more for thinking than for solving them. If you have trouble for solving them, I tell you the solutions. Indeed, I wrote it. Okay, so now let's go to the main goal of today. Is there something else I wanted to say? I guess no.
Would you define axiom A or you assume everything?
Today, not. And I'm not sure if I will define this. I think I will not need this notion in my course. Indeed, it would be nice to know if someone don't know what means hyperbolic, but if everybody know what is hyperbolic, you don't know what is hyperbolic? Yes. If everybody know what means hyperbolic, next time I will assume people know some of the hyperbolic theory, because the course is more on non-hyperbolic dynamical systems, going further, but using a lot of hyperbolicity. But today, I will remain in the topological level, explaining. So, as I told you, the first time I have seen a splitting was Smale, called the so-called spectral decomposition theorem. Indeed, I never understood very well why this spectral, but okay. But mostly 10 or maybe 15 years after starting to change my field to dynamical system, I have seen someone making mention of the fundamental theorem of dynamical system. And I had no idea what it was. And I asked to my colleagues at IMPA, which is a place where some dynamical system is done from time to time, and nobody knew what was the fundamental theorem of dynamical system. And then I look at it. I didn't know if the guy giving this name was naive or arrogant. And after understanding this theorem, I was completely convinced that it was true. That was a truly fundamental theorem of dynamical system, at least if you are not dealing with conservative systems. For conservative system, this theorem has no importance, is not interesting at all. But for non-conservative system, yes, it's fundamental. And that is what I will explain you, because I think still now, many people don't know it or think it's complicated, where it is a very fun theorem with a fun proof. And so I will give you the proof. Okay. So I have to start with the theory by Conway. So today I will state the theorem, and then I will start the proof. I don't know if I will do the proof today or with part of next Thursday. So my setting will always that I have H from X to X. So X is a compact metric space. So XD, the compact metric space, on A, homomorphism. We will see after that the theory works exactly the same if you look at flows. Flows are okay. Maybe if I don't forget, I will give some word about flows at the end. So the idea is first to define the weakest possible notion of recurrence. So you know, for students, to be recurrent means that your orbit is passing close to itself. But there is a weaker notion which is non-wandering. You are not asking that your orbit by itself go back, but there is a nearby orbit which is coming back. And maybe when you want that it's coming back means very, very close, you have to change this time your orbit. You have a sequence of orbits tending to your point. On this orbit have some return. Okay. Here we will consider a weaker notion. So it depends from some. We start with some epsilon positive, and we will consider what we will call epsilon orbit. We could call that chain also, but people usually say epsilon to the orbit. What is that? It's just a sequence. You have your starting point, x like x0, then you have f(h) of x0 that you allow you to make a small jump of epsilon. So you get some x1. So what we need, and then you continue by h, you get h of x1, and you allow to make some jump of epsilon less than epsilon. So formally, so you have xi, so that the distance between I plus 1 and the image of xi is less than epsilon. That is the notion of epsilon to the orbit. Yes. Also, we will say that the point x is chain recurrent. So let's say our chain. Just for explaining the terminology, because that is not my terminology, but people go from pseudo orbit to chain recurrent, because that is also chain. So X is chain recurrent if, by definition, for any positive epsilon, there exists n larger than 0 on x equal to x0 going to xn equal to x0 and epsilon to the orbit. Okay. And then we will consider the step. So we will denote by R of F the set of R of H, the set of all X which are chain recurrent. So once again, as it is very easy and better to do by yourself, I let you as an exercise the fact that it is a compact on H invariant. That is H of R of H is equal to R of H. Another exercise. But maybe someone can do just now, not adult people. If you consider on the circle some homomorphism which has a unique fixed point. And that a fixed H is just 1 point. So maybe you can see that this means, let's say, the dynamic is like that. So if you look at here, you have a unique a recurrent point. No point is going back close to itself, but what is the chain recurrence set? Some of the students is able to answer. Sorry?
The whole space.
Yes, because when you arrive, you iterate to go as close as you want at that point. Now you can make an arbitrarily small jump to the other side, and you can go back to your point. So that is indeed, you take the negative orbit here, and you make your jump exactly to the negative orbit, and you can close your pseudo orbit. Okay, so that makes that in general you have more chain recurrent point than the other notion of recurrence. Now, the idea is to split the dynamics. For the moment, we only define the place of points, the larger place that we can consider that interesting for the recurrence. But it's split in a natural way as follows. So, first, given if you have epsilon positive, let's consider the relation. I will denote like that, epsilon y, if there exists an epsilon orbit from X to Y. Okay, and then I will denote with no epsilon if that is true. If for any epsilon we have that you can go from X to Y by epsilon to the orbit. Okay, that so from this notation means you allow any small jumps, and you always can take iterate, making some jump, iterate, and so on, going from X to Y.
Maybe you don't want the sum epsilon, the second one.
Sorry?
You have the same thing. Or you erase the epsilon.
Yes, better. And if it is symmetrical, I will symmetrize my notation, so I will put like that. So if you can, if we have both, if you can go from X to Y and to Y, from Y to X. So I don't know if it is a theorem, but a proposition that this relation is an equivalence relation on the set of 10 recurrent points. And so the 10 recurrent, so the classes are the 10 recurrent classes. And they are compact and invariant. On the 10 recurrence. So with this proposition, we split this set where all the dynamic, which contain all the interesting dynamic in classes which are disjoint and compact and invariant. That's a decomposition theorem, but in fact, it's not just for that. That is truly easy, so I will not give the proof. You can check by yourself that this relation is compact, that the invariant is very easy, and okay. I will prove the proof theorem, which is just now, and which gives you the importance of this theorem, of this notion. So that's the objective of the day. So that is called fundamental theorem of the dynamical system. So you have H from X to X homomorphism. So I will give two versions of that, either X compact metric space or X smooth manifold, compact manifold, or closed manifold. Okay. So there is this. Then there is phi from X to R, a continuous map. Maybe I will change color for manifold. Then I will put here smooth.
Sorry, when you say manifold, you mean it's not necessarily compact?
Oh, you never listen.
No, I don't think so.
Compact, or let's say closed. I said compact, and then I rectify by closed. Yes. Okay. So if X is a manifold, you can replace, if you want, continuous by smooth. Okay. So what are the properties? So that First of all, for every point, you have that phi of h of x is smaller or equal to phi of x. That is, if you look at the dynamics, maybe I make the picture at the same time. That I make the statement so that we can follow. So you have your space, you have phi on R, and what we get is that for every x, h is going down. Or it can go to the same level. Okay, there are the two possibilities. You have equality. So let's put y, as I put a y in my picture, is phi of y. That is equivalent to the fact that y is chain recurrent. Okay. This one is because y is chain recurrent. If you have x and y, let's put the d on y, which are chain recurrent, then they have the same image, phi of y is equal to phi of z, if and only if they are on the same class. And finally, so if you take the image of phi, so here you will get a segment, okay? But on this segment, you can look at phi of the chain recurrent set. And what you will certainly, you will have the max on the mean, but you will have in the middle something, but you don't have any intervals. This one. Is the interior, so phi, is it possible to read here? Yes, phi of h as empty interior, contains no intervals. The first time, it looked like a technical condition, but indeed it's very important. So here, let erase here inside, but assume you have 2 points which are, assume that y and I don't know, y1 and y2 are in R of h and R of h, but are not equivalent. Not equivalent. So if they are not equivalent, what says the last item here is that there is some level between which don't touch R of h. We don't touch the chain recurrent set. So in this kind of level, every point goes down. So you get here some filtration where your 2 points are not in the same level. You are separating every class from some attracting region and some repelling region. Okay. So you see that it's a very strong properties. The last one, it truly allows you to split the dynamics by regular levels, and you look at what's remain between regular levels, and what you cannot separate by these levels are the chain recurrent point in the same class. It is a very strong structure. And so you start with homeomorphism on your Lyapunov. I forget to say that is called the Lyapunov function. Well, in fact, Lyapunov by himself wrote his name like but I think nobody do that now. So yes, because at this time France was more important than now, and so he wrote his name in the French style and not in an English style. So there are letters of Lyapunov with Lyapunov writing himself like that. Okay, so I hope you will be convinced that this theorem is really important and is fundamental. Fundamental, you don't want to say more important than other things. It's truly the first structure theorem, and which is completely general if you are not conservative, because if you have in some conservative setting, you have a unique class, and so there is nothing to separate, and so on. So let's go to the. It can be time to make the point, and then we will start the proof, or maybe with the proof. So. So Conley, it was in I will give a third characterization. So you see here we have first characterization by the chain, by the pseudo-orbit. Another is the chain recurrent class are what you cannot separate by Lyapunov functions. And there is a third characterization which use the oldest structure in dynamical system, well known by Poincaré, well used by Poincaré, which was the attracting regions. So so what is an attracting region? Or people say also trapping region, or trapping or attracting region. So I will take U a compact subset. So that H of U is contained in the interior of U. So you have U and H, that is U, and H of U has to be inside. Yes? Then, with this attracting region, so every orbit is going inside this region, and no one are going outside. So you can ask where they are going. So indeed, you iterate more and more and more, and you get as that is a compact subset, you get a decreasing sequence of compact subset, and you take the intersection. That's the place where your orbits are going. So you are looking. So I will call that AU is an intersection of the H n of U. You can take, either take n positive or n in Z. That will change the result. So let's put in Z. So that's the maximal invariant subset it will be called the attractor associated to U. So, more generally, A is an attractor. In this terminology, many times in dynamical systems, people want something more on attractor. They want some recurrence of the attractor. Here we don't require anything. We just require that, so for A being an attractor, for definition, A is an attractor if there exists U, so that A is the attractor associated to U. So that is attracting region, or trapping region. So you can define in the same way the notion of a repeller. A repeller is attractor for F minus 1, for H minus 1, for the inverse dynamic. But it's also that if you have U, which is so that's another exercise. I hope I'm not wrong. So if I'm wrong, you tell me. I remember that I had difficulty to do it when I start. So you take a trapping region, attracting region. So check that if you take the complement and you take the closure, that is a trapping region or attracting region for H minus 1. So as you can, so if I'm wrong, anyway, there is a canonical way for attracting region to associated an attracting region for the inverse dynamics. So you get that the attractor, if you look at the attractor for this attracting region for H minus 1, it will be a repeller canonically associated to so here the attracting, so you get an attractor for H minus 1. That I will denote by U, as it is canonically associated to U. And so I will speak on pair attractor repeller. If you have the pair AU RU. Okay. So you have to think to the dynamic like that. You have your space, you get an attracting region here, you have the attractor there. But if you look at the reverse, so now so here the positive image is like that, but the negative image is now like that. And if you continue there, you will get here. So here, that was U. That is a U, and that is a U. Okay? So the dynamics, mostly by this splitting, goes from the repeller to the attractor, and in between, everybody just go down. Okay. So that is the notion. So it will be important for me to notice that. So here is a compact. So you have your U, which is a compact set, and this one is in the interior. So I can look at plenty of compact subsets which are in between. If I look at this plate, if I consider D, so I continue with my exercise. If you look at V, which is in compact, so V compact, so that V is included in U and contains an interior of V contains H of U, then V is also an attracting region with the same and you have that A U on here nobody will see. So when you have that A B R B are equal to A U R U. In fact, the repeller associated to an attractor A do not depend on the trapping region which define your attractor. So the repeller is really canonically associated to your attractor. So you are poly pairs like that. Okay. So you take AU, you have plenty of open set for which it is an attracting region on defining this. On each time you go negatively, you get the same repeller. So the first, so let's go to a third characterization on that some parallel theorem as this one. On which is a main step, one of the main steps of proving the fundamental theorem. So always you have that H homomorphism from a compact metric space. Then a point is n recurrent that is equivalent to the following. For any pair A R of attractor repeller, you have to your point belongs either to the attractor or to the repeller. So in another way to writing, you consider what I will denote by A of H is the intersection on every pair AR attractor repeller and pair of attractor repeller of the A union R. The second, so that is for characterizing the chain recurrent point. And then if you take 2 points which are chain recurrent, then they are equivalent, they are in the same chain recurrent class, if only for any pair AR, you have that X belong to A if and only if Y also. So you will never have 1 point in the attractor, the other in the repeller. Sorry, I put exactly the contrary that I wanted to say. So this equivalence relation, chain recurrence class, can be defined otherwise. You say that X and Y are equivalent. Each time was one in some attractor, the other also.
Is this first equivalence also?
Thank you.
Thank you.
It's equivalent. So let's denote that X equivalent to Y. That's clear that it is an equivalence relation. Though the theorem is that these two equivalence relations are equal. Okay, so in some sense, you have the first idea in dynamical systems, so fundamental, for example, in Poincaré-Bendixson theory. So Poincaré-Bendixson, mostly, you say that if you have some recurrence of some orbits, then you get some circle transverse to the flow, so you have an attracting region. So that's a fundamental notion, the attracting region. And what say Conley is that you look at your dynamics and just with this unique tool. You don't have anything else. You can distinguish 2 points if you can separate them by an attracting region. And what you see is a chain recurrence set on the chain recurrent classes. Okay? So let's do the proof. So as it is here, some equality. So what you have to prove is that is equal to the recurrent set. So let's prove in some direction. So first, there is some easier direction that this one is included there. That is, assume take a pair, also here, an attracting an attractor repeller pair. And what happened in the point in the middle? Take X, which is not consider X, which do not belong to the union. Okay. So what you know here is that there exists some trapping region U for A. But you know, so you look at all the iterate of U. On the iterates are always disjoint from R, but what R is the maximal invariant set in the complement. So X is not in R by assumption, so it is in some iterate of U. So there is a first, but it cannot be in all. If it was in all iterate, it would be in A. So there is a first iterate, so that X belongs to HI of U, but not in HI plus 1 of U. Okay? Now you consider two things. You consider this distance. So you look at the distance between X and HI plus 1 of U. And you consider the distance between HI of U and HI plus 1 of U. That is the infimum distance here. The infimum of this distance. So you take some d smaller than 1/2 inf of these things. So you take some d smaller than the distance between X and H plus 1 and between the higher level to the lower level. So you look at, in some sense, so that is the distance of the gap, and that is the distance to X to the next step. And now you look at pseudo-orbit, consider pseudo-orbit, deep pseudo-orbit starting at X. So from X, you look at its image, it goes there. You are allowed to make a jump of size D. You cannot go further, so you have to remain at least in HI of U, and you cannot go closer than X to one from D. And now you take once again the image, so you go back below, and you each time you try to go back, you cannot go closer than D from X, and you cannot go up. So you all the time you are like that. So you have that. So let's say that its orbit is x0 to xn. So you have that for any n. You have that the distance between x and xn is larger than d, and xn belongs to hi of u. And with that, that is the induction hypothesis, and you get for next exactly the same.
I ask that second, the distance isn't HI plus 1 inside HI.
Better to put a -1. No, that it was I plus 1. And here it's HI. Okay, that is the complement x minus. Yes. To take the complement on that. You are completely true. I want to know the gap. So the gap, I need to look at the distance to the complement of HI of U to the complement to HI plus 1 of U. So thank you. Now it makes sense. Otherwise, it was always 0, which makes that was negative. Not a good idea. But now that it is fixed, is it okay? So the idea is always that with this, you allow this size of jumps, and each time you iterate, you go down from more than that. So the next step, you are allowed to change by D, but that is not enough for crossing or for going close to X. Nothing is enough. So you get so that this one implies that X do not belongs to F or H. That is, we just proved here. You don't have close to the orbit starting at X. So making contraposition, I don't know if it's an English word. In French, it's contraposition, so maybe it's English also. So this implies so that if X is in R of H, it is in this set. So it is also in the intersection of this kind of set for any pair. So we just prove that R of H is included in my set A of H. Okay. So we just prove that. So I promise you that it was fun, the proof, but that is not fun, it's natural. So let's see the fun part, just now. So that for the reverse, because you want to make so the contrary, so we want to say that if X is not recurrent, then there exists a pair so that X is not in the pair. So we need to build. The unique thing I know is X is not chain recurrent and I need to build an attracting region. So that's, I hope you will find that fun because for me, it's fun because it's a very, very simple idea. But if I ask you how you do that for the moment, I guess nobody knows. And when I will tell you, you will say, oh, just that. Okay. So the just that is that. So you will define, let's define for any X, you look at the set of points, so let's say W plus epsilon of X is the set of point Y so that you can go from X to Y by an epsilon law. Okay. You look at your point on where are you able to go? By this rule to make jump strictly less than epsilon. Oh, so I will, as I say, strictly, here it's open, so I will take the closure for getting some compact, or you change the definition, putting, no, that's a good, you take the closure. And the lemma is, it is an attracting region. You have no hypothesis on X, but for any X, W plus epsilon of X is an attracting region.
Every epsilon.
Sorry?
Every epsilon.
Well, if you take larger than the diameter of X, the attracting region will be X itself, my compact set itself, but it's always an attracting region. So everybody will say, oh yes, I knew that. Okay, it's not fun. But for the other, I guess that it is a surprise. And it's fully, I don't know, very simple. Why that? It's mostly by definition. How you build that? You start at X, you look at H of X, and you take the ball around H of X. Okay, now you take the image of the ball, and you take the epsilon neighborhood around this ball, and you continue like that. So now, if you take H of the union, you'd have to take the union of all that. Not X, but starting there, you take the union on each time the image taking the epsilon neighborhood. Take the image, take the epsilon neighborhood. You take the union of all that, apply H, so it's a distance epsilon from the boundary. Because you are allowed to take the epsilon neighborhood of the image and it's still inside. So that's trivial, but it's very strong. So that is the definition of, for me, of fun. When you see the proof, you say, does that? But before, you don't know. Okay? For me, it's magic, this part. Okay. If you don't believe me, better, you will try to do by yourself, and it's very easy.
Never assume a connectedness.
You don't assume all the assumptions are there. Compact metric is a unique assumption. Homomorphism for people doing non-injective dynamics. So no, here all is injective. Okay.
Insert the many components and that you have.
Oh yes, when you take
No, because can be medicine and no.
you have to take the union of everybody before being attacking. You have to take the union of everybody.
But after first image, it eliminates
So if someone prefers that I make all the epsilon as a blackboard, I do it. That's here, but I think it's better if you do by yourself. If you make the epsilon, I will transform something magic to something boring. But it's not large. My paper with all the epsilon is that. So it's not
how to imagine the base.
It's not difficult. Truly, it's just writing. You take some point in the closure, so but I think it's better just to make the detail by yourself. Okay. So now, well, if you have that X is not, so let's make the other inclusion. If you have that X is not recurrent, by definition, is that there exists epsilon so that X do not belong to the epsilon of X. You cannot go from X to itself by epsilon to the orbit. But if you look at X always belongs to the future of its past. So, and that is nothing else that, so that is the complement is a trapping region for the repeller. So, this is, say you that if I look at the, so let's say A, the attractor in W plus epsilon of X, and R, the corresponding repeller, so this repeller is in, it includes in X minus these things. And so X do not belong to the pair AR. which makes the reverse inclusion. We check now that, so that's say we already proved this inclusion. Now we see the other inclusion. So it's important. Okay, so that makes the first part of this theorem. On all the trick, the one direction was completely natural. The other direction was this trick that to every point you have some kind of canonical, given some epsilon, you have some canonical attracting region associated to it. And the point is not recurrent, it's precisely not belonging to this attracting region associated to your orbit. Okay. So let's finish the second part, that is to look at the fact that the equivalence relations are the same. So now consider 2 points, X, Y. And so first we assume that, so we can assume that they belong to the chain recurrent set, because it is equal to this set done with pair of attractor repeller. And we first assume that there exists a pair so that they are not in the same. So let's say that X in A and Y in R. So we have this picture. We have an attracting region. We have A here, R there. We have Y in this side, X there. Well, you look at so you have this attracting region U, you have H of U. And now if you look at this distance, there is the distance between X minus U and H of U. And so any epsilon so you take J is equal to 1/2 this one, any H of the orbit starting at X remains in U, you can never jump out of U, and then you cannot go to Y. So okay, so I said here, I just proved that if X, Y are not equivalent for this relation of always being in the same attractor or repeller in any pair, then they cannot be equivalent. Okay? So that is one of the directions. The other direction is with the same trick as here. So if you assume now conversely, you assume now that X, Y are non-equivalent. But you assume that you cannot go, but not equivalent. Let's say that you cannot go from X to Y. So that is, there exists epsilon, so that y do not belong to plus epsilon of x. But here, as it is chain recurrence, you have that x belongs to its own epsilon of x. We know that x and y belong, so in the picture, we have my x. With that, I make all the place where I can go by pseudo-orbit. But I can go to x itself. So if I look at on that, make me a trapping region. So this trapping region contains, so that is my W plus epsilon of s. On the attractor, x has to belong to the attractor or to the repeller. But it belongs to the trapping region here. It just can be in the attractor. So I have the attractor here. On y do not belong to the trapping region, so y has to belong to the repeller. So it was that y belongs to R and x belongs to A. So we finished the proof. Okay, that is this theorem, which has this nice idea that that are trapping regions, and is the main idea. Okay. I think I will need to finish next time. So let me make some lemma, which will be useful next time. So next time I will start by finishing the proof. That is by building the Lyapunov function. I think that doing it in 10 minutes means that we will accelerate on but not the spirit. So I will finish next time. So let's make a last tools. If you look at the set of pairs A R pairs attractor repeller. So this set may be infinite, but it cannot be more than countable. So a pair is associated to a trapping region, and trapping region are not countable. But to each trapping region, you associate a pair. But luckily, many trapping regions define the same attractor. So making possible that. And so what's the proof? The proof is you will, sorry, I'm working in X and D compact metric space. So there exists ON and in N countable basis of the topology. It means that any open set is union of open set in that family. Okay? So now if you take some, your set X, and you have your mapping region U, you have H of U. Okay? And then you can, from each point here, so that's a compact set, but from each point there exists some ON containing the point and contained in a U, in the interior of U. So you can cover this set by, as it is a compact subset, you will extract a finite cover. You will have I finite included in N, so that the union of the I in I cover the H of U. I can take here, I can take that, sorry, I will take and I can assume that its closure is included in the interior of U. Okay, so now I get that the union of the OI of the closure is a trapping region. A trapping region. And I have that the attractor associated to this union is equal to the attractor associated to the initial trapping region. So for any trapping region, I can take I can assume that its trapping region is on this form, union on finitely many of these countable. Okay, so now that gives the proof, because for getting all the pair attractor repeller, I only have to consider finite subset of a countable set, and that is a countable. That's the proof. And so for next, we will see how to build a Lyapunov function for any pair attractor repeller, and then to associate it to the chain recurrent set, separating every class. Okay, and then I will change the subject for going to smooth dynamics. I think I'll finish there, if I'm not wrong.
And have uncountably many chain recurrent.
Yes.
But there are only finite number of attractor repeller pairs.
Countable, yes.
Sample set and try.
So chain recurrent classes are you take any sequence of pairs of attractors repellers, and you make the intersection of either attractor in each pair you choose. If you make the intersection with the attractor and the repeller, and the result is your class. And so as you have countably many classes, but now you make intersection of all, so you get uncountably many. And so we will see that, yes, we cannot avoid the case of uncountably many classes.
half an hour break.